Hi, my name is Anirudh Krishnan. I am a master's student studying robotics at the University of Maryland. In this documentary, I will share my experiences of going through ENPM809T, autonomous robots, where I build an autonomous robot and take on the grand challenge. The grand challenge this year is inspired by planetary exploration. The robot, deployed on an interplanetary mission, has to find and retrieve certain items from a cluttered environment. In this case, the items are colored blocks like this one. The map of the environment is known to us and looks something like this. The robot has to move from its landing zone into the cluttered environment, pick up the blocks that it needs to, red, green, and blue in that order thrice, for a total of 9 blocks, and transport them to the construction zone. The environment also has adversarial blocks of different colors, black, white, and yellow, which are meant to confuse the robot. If any of these blocks are brought in, they cause points to be deducted. The entire challenge must be completed in under 10 minutes, and piercing the boundaries of the arena causes an instant end to the competition. To take on this challenge, the robot needs to have several capabilities, which are summarized in this diagram. Broadly speaking, the robot needs to be able to perceive its environment, to be able to identify objects and detect boundaries. It then needs to be able to move up to blocks and pick them up. It needs to know how to set and reach target positions on the map and build a list of actions. Finally, it needs to know how far it's moved and where it is within the area. Each week of the course, I assembled the hardware and wrote the software to build up this list of features to get the robot ready for the challenge. Now I'll talk about how I went about building the robot. The robot is based on the DF Robots Baron platform. It has a metal chassis with 4 wheels. Each wheel has individual DC motor powering it. An interesting feature of this robot is the kill switch we have to put on it in case the robot misbehaves during the grand challenge and needs to be turned off abruptly. The robot uses geared DC motors with a ratio of 120:1. The additional torque is handy because once all the parts are installed on the robot, it becomes quite heavy and challenging to move and turn. This video shows one of the 2 optical encoders on the robot. There are one on each side of the robot. The encoders make it possible to count wheel rotations precisely. The motor and the grippers are powered by external rechargeable batteries. Here is a video of the Baron chassis being assembled. The main computer, a Raspberry Pi, is powered by this 5-volt USB power supply. I made some 3D prints to help with further assembly and to keep everything in place. Here is a model of what the final battery enclosure looked like. The motors require too much current for them to be driven by the Raspberry Pi directly. The motor driver IC takes command signals from the Raspberry Pi and directs power from the batteries to the motors. This is a plate that I used to support the motor driver, which had a lot of external content. The main computer on the robot is this Raspberry Pi 3B Plus. It processes most of the sensor signals and produces all the actuator commands needed to drive the robot. Because of the number of exposed contacts, I decided to 3D print a case to shield the Raspberry Pi. The robot uses an RGB camera as its primary vision sensor. This one is from the Raspberry Pi Foundation and is compatible with Raspberry Pi. The ultrasonic range sensor uses time of flight from ultrasonic pulses to gauge distance. To avoid the usage of a breadboard on my robot, I integrated the circuitry that powers the ultrasonic sensor into the wire. This is a 3D printed mount that held the camera and the ultrasonic sensor at the front of the robot. This is a time-lapse video of me assembling the components in the upper part of the Baron chassis. The Arduino Nano is the second computer on the robot. Its purpose is to interface the IMU with the Raspberry Pi by USB. I avoided the use of another breadboard and created modular connections for all my sensors using this perf board circuit. I had to insulate the bottom contacts to prevent any short circuits. This is what the final modular circuit looked like. This 3D printed array of standoffs helped me with cable management. The IMU, or the inertial measurement unit, is the most important sensor for accurate locomotion on this robot. Once I realized the IMU functions best at the centroid of the robot, I 3D printed this stand so that I could move it and place it safely. This is where its final position was. The servo gripper is the end effector of the robot, and it is how blocks are picked up. This time-lapse video shows how I assembled the gripper and positioned it on the robot. Because the gripper was suspended on two large standoffs, this additional 3D printed structure helped strengthen the gripper and prevent wobbling. This is a 360 view of what the robot looked like on challenge day. Now I'll tell you how I use the Python programming language and the hardware you just saw to build out the capabilities of the robot. Using the PyCamera Python library, I can get a continuous stream of images from the Raspberry Pi's camera with high computational efficiency. This application combines the Raspberry Pi camera with the ultrasonic sensor to look at an object and tell you how far it is. While it was fun to create, it was not practical for the grand challenge because of the cluttered nature of the environment. The sensors used, especially the range sensor's distance reading, are noisy and hard to use directly. Using a moving average on the data allowed me to get usable measurements. Another analysis was performance testing of the Raspberry Pi when using image processing techniques, which helped me identify and mitigate computationally expensive processes. Using image processing techniques on the images makes it possible to understand objects in the scene and act on them. The application here uses HSC masking to pick out the green traffic light and follow it. The next application isolates the arrow with masking similarly and uses corner detection and some basic geometry to identify the direction in which the arrow points. The motor driver IC makes it possible to control the direction of rotation using DC voltages. Instead of DC voltages, if I use a PWM signal, I can also control the speed of the motor. I use the Pygame programming library to read key presses continuously and teleoperate the robot. The gripper of the robot is actuated by a servo motor, which changes positions based on pulse width. The wheel encoders let me count fractional wheel rotations. Counting encoder is how odometry is performed. Because the robot is in a kind of differential drive configuration, I can count opposite encoder counts to turn specific angles, though this is not highly accurate. Controlling the difference in the counts between the left and right encoders helps straighten the motion of the robot, as seen here. This is turning solely on the basis of the encoder ticks. It is not very accurate and not too repeatable. The IMU measures linear and rotational acceleration, but I only use it for the yaw value. This fused with the encoder measurements allows me to move in a straight line for long distances and turn with high accuracy and repeatability. One requirement of the Grand Challenge is to capture an image and email it to the professor when a block is picked up. I use the Python library YAGmail, which requires the Gmail app password to make it work, to enable this. Now I'll show you some of the complex behavior I created by combining the basic elementary functions that you just saw. The robot's fundamental move function translates it by relative distance or rotates it by relative angle. The more useful navigate function, which enables Cartesian positioning of the robot, is built from 3 moves, 2 rotations and 1 translation. Here I highlight parts of the image that look like blocks. This uses HSV masking and contour creation to draw bounding boxes. It also uses contour area filtration to disregard small patches of the target color which might confuse the robot. Distance estimation is the groundwork for block tracking. I use bounding boxes because I'm interested in using the width of the box to map it to distance. This video shows my calibration and curve fitting process. To estimate the angle to turn to center a block in my camera frame, I need to understand how far the block is and how many pixels the field of view is at that distance. Using basic trigonometry then lets me calculate the angle that I need to turn to center the block in my frame. This video shows how distance estimation and angle estimation are used to track the block. Once I'm able to follow the block in my frame, it's not too challenging to move to the block and pick it up now that the gripper and navigate functions are also established. Hi, I'm going to explain how my robot scans for blocks. From the initial position, it moves to the first relay point. At this relay point, it scans through 5 angles that cover about 150 degrees. If no block is found, it means that the blocks are too far to meet the robot's threshold or no blocks are present in the area. It then moves to the next relay point and repeats the 5 angles that it scans through. If no block is found, the robot moves through all the relay points searching for blocks. If no blocks are found at the last relay point, it means that there are no blocks within the area or the robot has failed to detect a block. A part of my move function is to view and update the robot state, which is the Cartesian position of the robot. This example shows you how the robot moves through a rather convoluted path, and I'm still able to extract the Cartesian path and plot it. The robot slips when it turns, and this is not accounted for by any of the sensors. To solve this, when a block is placed during the grand challenge, the robot is at the edge of the construction zone before it enters it. It will now stop to turn to two directions highlighted in red and check the range sensor distance measurement. This will help it compensate for any drift in its internal state. A common problem to many challengers was the constant adjustment of the HSV mask values under various practice lighting conditions. I solved this by calibrating my mask with images taken from the competition arena under expected lighting conditions and storing them for the day of the Grand Challenge and enabling them during the Grand Challenge. There is a discontinuity in the readings from the IMU when turning right from 0 degrees or left from 360 degrees. My eventual solution to this was to use a system of left and right error bounds determined before each turn, and also to find the shortest path from any given angle to any given angle, even if it means passing over the discontinuity. This is the problem of oscillating when centering a block once the block has gotten too close. To solve this, I dynamically expand the threshold, which triggers a turn towards a block the closer I get to it. The IMU and range sensor have to be constantly polled to get values from them in real time. This causes their usage to be blocking to the main thread of the program. Using multi-threaded programming and object-oriented programming solves this, but introduces a hidden error which caused my range sensor to shut off during the grand challenge. If an error occurs in a thread, it will stay buried till the program ends. This is my run through the grand challenge. My robot has a strategy of dealing with blocks that aren't the target block. It always goes to, it always picks the largest block that it sees. If the block that it has picked is indeed the block that it needs to continue the grand challenge, it will transport this block via a relay point into the construction zone. If the block that it sees is a friend block, which is a beneficial block but not the block it needs for that point in the grand challenge, it will place it in a safe zone. The safe zone is checked anytime the robot has to pick a new block. The adversarial blocks are not picked and are basically run through because their masks are not included in the block's vision. So at this point, my robot knocks down a block that it's trying to pick, and it goes into an infinite loop of trying to repick the block. Since a toppled block cannot be repicked, this is how my grand challenge ended.